Given an array of integers, find out whether there are two distinct indices I and j in the array such that the absolute difference between nums I and nums j is at most t, and the absolute difference between I and j is at most k. How would you do that? That's about today's video. Let's get into it. Alright, here is follow-up number 3 for this contains duplicate series of problems, contains duplicate number 3. Given an array, let's look at the slight variation of this follow-up question. Given an array of integers, find whether there are two distinct indices I and j in the array such that the absolute difference between nums I and nums j is at most t. So we're adding one more condition here. So it's asking us for the absolute difference between the values, the numbers of this array is at most t. So the condition that we got added on the second follow-up is that the absolute difference between the two indices is at most k. So now we have one more condition added, which is the absolute difference between the values, the two values, is at most t. It's actually not duplicate. It's asking us for looking for the difference, but it's similar to the previous two questions, so it's called contains duplicate 3. Let's look at a few examples. This example, 1, 2, 3, 1. K is 3, meaning the two indices should be at a max of 3, and t is 0. 0 basically means the two numbers are exactly the same. They're duplicates. There is no difference, right? 1 and 1. The difference is 0. Max is 0. So, and the k max index difference is 3. So it's 1 and 3. No, this index is 0 and this index is 3. So the max difference for the two indices is 3. That's why this one is returning true, right? So still, let's take a look at the second example. Second example, the max difference for the index is 1, and the max difference for the two values is 2. So this one is a good match, right? So the max difference for these two is only 1 for indices, and the value difference is only 1 as well, which is lower than t. So the return is true, right? Which is valid. Now let's look at a negative example, which is this test case. 159, 159. The max difference for indices is only at 2. So we can look at up to this, 159. But the max difference for values is at 3. So that's the difference for values. So 5 minus 1 is 4. 4 is greater than 3. Okay, it's not going to work. 9 minus 5 is 4. Okay, 4 is still greater than 3. So it's not going to work. The same is true for the rest, right? For the rest, it's always 159, 159 in this hash set. So there is no possible pair or possible range that contains such two values that could meet two conditions, both conditions. So that's why it's returning false. And let's think about how we can tackle this problem. It's basically a follow-up. So let's continue our solution, our algorithm, our ideas for the solution for problem number 2, for follow-up 2, which is we're using a sliding window or a hash set of a fixed size of size k. Let's think about that. So we'll continue to use that. We'll still use a hash set. Say the hash set size is going to be 3 in this case. Hash set size is going to be 3 in this case. Then what we just got added one more condition, which is to check whether the max difference for values is at max of t, right? At max of t. That's the additional condition that we will need to check. Then how can we do that check to check the value for to check the difference for the values is within the boundary of t? How can we apply that check? Let's just take a look at this example, 1, 2, 3, 1, with k equals to 3, t equals to 0. Let's see here. This is the index, 0, 1, 2, 3, for these 4 elements in this given array. So we'll continue to use a set. The set size is going to be constant, which is k. In this case, it's 3. So we start from the very left. Start from the very left end, 1, 2, 3. This is what we get for our initial hash set. for our initial set. Then the set here, 1, 2, 3, we don't find any duplicates here, right? So then what we'll do is that we'll continue to add one more here. We add one more 1. So now the hash set becomes this. Remember, in the solution for our previous follow-up, which contains duplicate 2, there are 2 steps. First, we try to add the element we're iterating on into the hash set. If it cannot be added in, we just directly return true, which means we found the duplicate, right? However, if it cannot be added into the hash set, we do a second step, which is to check the size of the hash set. If that one is greater than k already, we're just going to remove the oldest element, right? In that case, we're going to remove this one. So we'll continue to follow that idea to have a set of a fixed size of size k, right? And then what we will do is still we'll have 2 steps, but we'll reverse the sequence of the order of the steps a little bit. First, we will check. Here we have a set size of 3. Step 3 is that before we iterate, when we iterate on this element 3, the size contains these 3 elements at this point. What we would like to, so remember we got added one more condition, which is to check the max difference for the values. So at this moment, what we would like to check is whether in this current set is 1, 2, 3, whether there exists such an element that either it's smaller than or greater than this element that we are currently iterating on. Anyway, the difference between this and any one of the elements is within the boundary of t. It could be greater than this one or smaller than this one, but the difference between that element and this one needs to be within the boundary of t. If there exists such an element, whether it's smaller or bigger, then we can just safely break out, we can return true, right? So only 2 cases, whether it's greater than this element or it's smaller than element. So this question boils down to whether there is an efficient data structure or that could give us the quick access of, like say, better than OK. K is the size of the hash set, right? Better than OK time complexity to give us access to what element? To the element that is the minimum element that is greater than this element, or the maximum element that is smaller than this element. That is what we are interested in. Of course, we can always do a linear scan, which is the size of the current set, which is k. That's not going to be very optimal. Actually, if we just do that, we don't need any other additional extra data structure to help. We can just write a nested for loop, right, to iterate through this. That's going to result in time limit exceeded. Your code is not going to be accepted. And actually, that's not very optimal if you come up with such a solution. Of course, that's a brute force solution. It's workable, but of course, it's not going to be accepted by OJ or your interviewer in the real interview. Then how do we solve this problem? Which data structure? Of course, we're going to utilize an additional data structure, but which data structure is going to give us very fast or efficient access to get the max value that is lower than the current element, and also the mean value that is greater than the current element? Which data structure is that? We're not going to use an array or a list or a linked list. In that case, it's going to give us ON. With the n is the entire length of this list or array, right? What we're going to use is a binary or self-balancing binary search tree. Why do we need a self-balancing binary search tree to give us faster access? For example, let's look at this. This is just an irregular array or linked list or whatever. In order to find the max or mean value of this collection, we need to go through this entire array once. So the time complexity is going to be ON, right? However, for binary search tree, we know all of the children nodes on the left is guaranteed to be smaller than the root node here, and all of the children node on the right side is guaranteed to be bigger than the root node here. So when it's a self-balancing binary search tree, which means when we do insertion or deletion, it's going to self-balance out. which means it's going to restructure this tree to keep the binary search tree to meet its definition, meaning all of the left are smaller, all of the right are bigger. So that means that's going to give us faster access and deletion and insertion, right? So this one is going to give us OH, time complexity. OH. H stands for what? H stands for the height of this tree, which equals to O log n. O log n. N stands for the total number of elements in this given array. This just drastically improves time complexity of insertion and get, right? This is basically improving from n to O, from On to O log n, from linear time to logarithmic time. This is great improvement. This is what we are actually going to need. This is how we can come up with a solution that gets it accepted on OJ and gets accepted, gets a smile from your interviewer. Okay, that's the idea. How can we put that into actual code? In Java, there is a data structure called tree set. So it's still a set, but it's called tree set, which internally it's giving us O log n time complexity for doing basic operations. For example, remove, get, all of these basic operations. It's guaranteed to give us O log n time complexity. So we're going to continue with that, and let's implement the code. Oh, one more thing to note is that we need to use long instead of integer. Why is that? Because, for example, here, one case is that what's the max value? Say, the max value, we'll just call it what is integer max value in Java? That is this number. So one case that we need to consider is that if we get this number and we need to do, for example, a minus operation of this number. So, for example, we are given two numbers. One is this, the other is this. And k is 1, just in case, just for example, let's assume k is 1. T is this number. T is this integer max value. In this case, we know that it should return false, right? Because we are given these two numbers, which is integer max value in Java, for example. And the size is only 1. The size of the set is only 1. And the max of the difference between the two indices is at max 1, which is okay. So we meet that condition. So there are only two elements. The difference is 1, 0 and 1. That's fine. And the difference for values is at here. So we know the difference between these two numbers is actually what? Is actually this value. This value times 2, right? That is the correct difference between these two values. However, if we just use integer, what we will do is we'll use this number to minus this number. If we just do integer arithmetic operation, it's going to overflow. It's going to give us, I believe it's going to give us minus 3, but we need to double check. But anyway, it's not going to give us the correct value. Of course, minus 2 is smaller than this number, so it's going to return true. But actually, it's not true, because we know the actual difference between these two numbers is actually this one. This one exceeds the upper limit, the upper boundary of the integer max value in Java, right? So in that case, what are we going to do? We'll just convert everything into long type, which is much bigger than integer. In that case, we will avoid the overflow situation. So let's consider that, put that into code, everything, like the algorithm and considering integer overflow situation. Let's put that into code. Tree set. As I said, tree set is going to guarantee to give us O log n time for basic operations, get, delete, insert. All right, let's do that. Integer set new tree set. Next, what we will do is This is all exactly the same as the previous two solutions for the previous two questions. But the two steps are going to be a little bit different. So as I said, what we will do is we will find the max value in the tree set and the mean value of the tree set inside the tree set. Then we'll check the difference. So, instead of integer, we'll use long. Okay, so we'll get long. In tree set, in Java implementation, there is two very handy APIs called ceiling and floor. Let's use that. Set floor, which is the current number that we are trying to iterate on. So floor is going to give us, think about it's the floor. So it's going to be the minimum, it's actually the maximum value that is smaller than the current value. Okay. It could, if it doesn't exist, it's just going to return null. So we'll check first if floor not equals to null. And remember that's the maximum value that is smaller than. So we're going to use nums I minus floor is smaller than t. If that's the case, we're just directly going to return true. That means we find there is such a pair that the maximum difference between these two values is within boundary of t. All right, then we're happy. If that's not the case, we're going to check the minimum value that is greater than the current value. The minimum, okay, that is going to be called ceiling. Ceiling of the tree set, nums I. Also, we'll check if ceiling is equal to null. If it's not, what we'll do, that's the minimum value that is greater than nums I. So we're going to use ceiling minus nums I. Check if that one is greater than or smaller to within the boundary of t. If that's the case, we're happy too. We can just return true. Otherwise, if these two cases are not met, that means within the current tree set, we didn't find there's such a possible value that is within the boundary of t that could have a difference to the current nums I. Okay, then what we'll do is that we basically fall to step one of the previous two solutions. What we'll do is try to add that into, we will add that into the tree set, which is set add nums I. Another step is that we will check if set size is greater than k. If that's the case, remember here, what we do is that we will remove, right? Now we're at this step. We have added this 1 into the tree set, but then we check the size of the tree set is actually 4. 4 is greater than k, which is 3, right? Then we will remove the oldest one, which in this case is I. How do we denote the index of the oldest element, which is exactly the same to the previous solutions, which is set remove nums I minus k. That's it. That's the solution. That's the algorithm. And after that, if we have gone through all of this, we never broke up from these two conditions. That means we didn't find such a pair. There's no such duplicates. All right, and then we'll just return false. That's it. That's the entire algorithm. Let's hit submit and see. Oh, okay. I need to convert it. Forgot that. Long. This to be long. This needs to be long, and this needs to be long, and this needs to be long. Let's hit submit and again. All right, accepted. Now let's talk about the time complexity. The time complexity is going to be O n. Of course, there's going to be n. N is the number of elements in this given array, right? But then we have another cost, which is to do the floor, the ceiling, and add and remove. All of these costs, since we're using a tree set, is giving us significant improvements already over performance improvements already over a linear scan, right? But still, it's not constant. There is a time complexity over here, so it's going to be log, as I said, it's going to be log h. So this h in this case is going to be the minimum value of both n and k, right? K could be greater than n, which kind of odd, but that's possible. So we'll use the minimum of n or h or k, which is the time complexity. That's the maximum height since we're using a self-balancing binary search tree. Think about this. This is the OH, which is O log minimum of n or k. That's it. That's the time complexity. Okay, now let's talk about the space complexity. The space complexity is basically just this tree, right? Let's take a look at this self-balancing binary search tree. This is all of the nodes. They need space, extra space or memory to hold all of the values of this self-balancing binary search tree. So that is going to be ON, right? Which is, in translating that into this context, which is going to be N or K. The minimum number of either n or k. K could be greater than n, so we use the minimum of either n or k. That's the max, because at any point of time, we're only going to hold at a max of k elements. So k could be greater than n, so we take the minimum of n or k. At any point of time, this tree set contains only the minimum number of n or k. That's the space complexity. That's the extra memory that we're going to use for this entire run of this algorithm. So that's about the solution for this problem. Of course, there's even more solutions, for example, using bucket sort, but we're not going to dive into that. If you're interested, feel free to go to Discuss board. There's a wonderful discussion over there. People post solutions over there. So if you feel you learned something from this video, please do me a favor and gently tap the like button. That's going to help a lot with the YouTube algorithm. And don't forget to subscribe to my channel. I would really, really appreciate it. Just destroy the subscribe button. I'm going to appreciate it a lot. Again, thank you so much for watching this video. If you have any comment, please do me a favor and leave any comments, feedback down in the comment section below. Then I will know where I can improve. Thank you so much. I'll see you guys in the next video.